Hi, welcome to Chapter 5 and Video 5.1a, Introduction to Derivatives of Natural Log Functions. So in Chapter 5, we'll be studying log functions, derivatives of log functions, integrals yielding log functions, inverse functions, and exponential functions, and again, derivatives of and integrals of, and at the very end will be inverse trig functions, but that's after we finish everything else. Okay, so 5.1 is the natural log function. That's y equals ln x, which means y equals log base e of x. Keep in mind that the logarithm, you can only take the logarithm of a positive number. So the base always has to be positive, and the number you're taking, the logarithm of, has to be positive. Now, of course, what this means is just another way of writing that the base e to the power of y is equal to the answer of x. Okay, so properties of logarithms. These are very important properties that you learned back in Algebra 2. The ln of 1 is equal to 0, and the main reason for that, of course, is if you take e to which power equals 0 equals 1, e to the 0 equals 1. Very powerful theorems, these next three theorems. The product property, that the ln of a times b is ln a over, plus ln b. The ln of a over b is ln a minus ln b, and the ln of a to the power of n is n times the ln of a. Now, the way we're going to use these theorems, think about it when it comes time to take a derivative. Would you rather do a product rule or just add two derivatives? Would you rather do a quotient rule or just subtract two derivatives? Would you rather do a chain rule or just multiply by a constant? So before you take the derivative, you're going to use your log properties to make your life easier. Now, there are three that they haven't. I mean, they have ln of 1 is 0. They should have ln of e. Again, base is e here. E to which power equals e? Well, obviously, e to the 1 is equal to e. Now, this is a weird one. This is e to the power of log base b of x. It is equal to x. And kind of let me show you that over here. This is e to the log base e of x. If we let y equal log base b of x, then I can replace that by y. But of course, if log base e of x is y, that means e to the y is equal to x, and therefore you get x. Basically, if this base and the logarithm base are equal, then this answer will be whatever you're taking the logarithm of. ln of e to the x, of course, is x, because you're asking yourself e to the which power equals e to the x. Well, of course, it's e to the x. Now, the number e itself, which is 2.718 dot 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 non-terminating, non-repeating, is an irrational number. The definition of the number e, highly unlikely in AB they'll ask you about that, but it is the limit as n goes to infinity of 1 over 1 plus n to the n. This is a similar formula. You'll notice instead of 1 over n I have t, instead of n I have 1 over t, instead of n goes to infinity. Well, obviously if n goes to infinity, then this expression, which is t, goes to 0. But if we take this first one, if you took the number 1, 2, 3, etc. for n and you plugged it in, this would be 1 plus 1 over 1. So if you were to take this expression 1 plus 1 over n to the n and you replaced n by 1, you'd get 1 plus 1 over 1 to the 1, which is 2 to the 1. If you replaced n by 2, you get 1 plus a half, which is 1.5 squared, which is 2.25, etc. As you keep going down this list, it'll just keep getting closer and closer to this famous number right here. Okay, so here's our first formula for chapter 5, the derivative with respect to x of the ln of x, and right now we're only dealing with natural logs, log base e, is a very simple formula, 1 over x, okay? Obviously, if instead of pretty little x, we have its ugly or distant cousin, then we're into the chain rule. It's going to be 1, just like here, it's 1 over x. Here, it's going to be 1 over u, but because it's ugly, we're going to multiply it by du dx. Now, one way to think of this is, obviously, since this is 1 over and you're multiplying, this guy will end up being your numerator. So we often won't write 1 over times. We'll just write the derivative on the top over u. Make sense? Okay, so here's a perfect example. d dx of the ln of x squared plus 3. The long way would be it's 1 over x squared plus 3. It's 1 over the u times the derivative of that u, which is 2x. I would think you could go directly over here. Picture it's going to be 1 time, so just leave a space up there, over x squared plus 3 times, and then write the derivative of your denominator on the top. Now, an example like this, yes, you could start taking the derivative right now, but it's going to be a heck of a lot easier if you use your log properties and pull that stupid 5 out in front. And then that 5 can go all the way out in front, which means now you're not taking the derivative of 2x cubed minus 7 all to the fifth. You're just taking the derivative of 2x cubed minus 7. So that's going to be 5 times. And remember, the derivative of the ln of a thing is 1 over that thing. So 1 over 2x cubed minus 7 times the derivative of our u, which is times 6x squared. Okay? And then I'm just simplifying that a little bit. All right, so now we're just going to use that formula ad nauseum. Find the derivative of the function. So this comes out of the textbook. The question is y equals x times ln x. This is an example. So it's a product rule. Pay attention to that. So it's the first factor times the derivative of the second factor. Derivative of ln x is 1 over x plus the second factor, which is ln x, times the derivative of the first factor, which is 1. These x's cancel, and you're left with 1 plus ln x. Okay? Here's another example, y equals the ln of the square root of x squared minus 4. So again, what you're going to do here is the first thing you're going to do is you're going to simplify this log expression before we even take the derivative. And that's going to be a few lines. Notice it's still y equals. So the first thing I'm going to do is write it to the power of a half. Then I'm going to use the log property and bring that half out in front. Now I'll take the derivative, because now it'll be easier. So I have 1 half, and then I have 1 over x squared minus 4, and then chain rule times the derivative of x squared minus 4, which is 2x, and you'll be left with x over x squared minus 4 as your derivative. Here's another one. This is the ln of x. So if you think of it as the ln of u, it'll be 1 over u du dx, but our u happens to be ln x. So we're taking the ln of something, and we want the derivative of the ln of something. So it's 1 over that something times the derivative of that something. Well, the derivative of ln x is 1 over x, and you're left with 1 over x ln x. Very easy stuff. Okay, here's another one. You have the ln of a product, and there's a power in there. So the first thing I'm going to do is break up the product. I'm going to call it ln t plus ln of t squared plus 3 all cubed. But then for the second one, I can pull that 3 out in front. So now it's a lot easier. There's no product rule. There's no complicated chain rule. This is an easy, tiny little chain rule. So now I'm going to take d dt of each side. I'll get dy dt. Derivative of ln t is 1 over t plus 3 times. Derivative of ln of this thing is 1 over this thing times the derivative of this thing. And then you'll simplify and you'll find a common denominator. I'm not going to spend my time doing that. That's algebraic simplification. That's algebra 1. Number 58, again, find the derivative of the ln of 2x over x minus 3. You could just leave it like this, and this will be a 10 times more difficult problem, or you can make your life a lot easier by replacing ln of a over b by ln a minus ln b. Now, there's no quotient rule, so now we're ready to take the derivative. Derivative of the ln of a thing is 1 over the thing times the derivative of a thing, minus derivative of the ln of a thing is 1 over the thing times the derivative of that thing, which happens to be 1, and you're left with that. Now, of course, you could simplify that, find a common denominator, blah, blah, blah. Now, this one, there is no properties I can use, okay? If you have the ln of a quotient, you can break it up into a difference, but this is just ln t over t. So I have to do a quotient rule here. So I have denominator squared, I have denominator times derivative of numerator, which is 1 over t, minus numerator, which is ln t, times derivative of denominator. The t's will cancel, and that's pretty well what you're left with, 1 minus ln t over t squared. Here's the ln of the cubed root of x minus 1 over x plus 1. So the first thing I'm going to do is rewrite that as the ln of x minus 1 over x plus 1 to all to the 1/3. And then I'm going to bring that 1/3 all the way out in front. And then I have the ln of a quotient, which becomes ln numerator minus ln denominator. So that's going to be a heck of a lot easier is to take this expression and rewrite it using log properties before I take the derivative. So now I have 1/3. The derivative of ln of a thing is 1 over the thing times the derivative of the thing. minus, same idea, derivative, the 1 over x plus 1 times the derivative of x plus 1. And then you'd simplify.